Good morning, class. I hope you're enjoying the PSAT test, because we're enjoying class here on a non-chapel day. Anyways, welcome back to Chapter 6. We're going to cover these terms today. Most of these are on your really cool periodic tables, which we just finished looking at, so don't be embarrassed. We didn't critique you too much. And question?
I didn't receive mine.
Good. Let's do the stack and find yours then.
Thank you.
Unless yours was one of the ones that didn't have a name
Yeah,
on it.
mine didn't have a name on it.
I need to give you credit for it, and I'll get back to you tomorrow. Okay? Okay, so yesterday we started talking about two guys. Who's the guy that gave us triads? Quick review question. His name is Dobereiner. Everybody say Dobereiner.
Dobereiner.
Yeah, big long German name. And then we talked about the father of the periodic table. What was his name? The guy in Russia who wrote 1,200 miles on a horse, and then 400 miles on a horse, and finally got accepted to Duke College. Mr. Jackson. Mendeleev. There is an element named after him now. It took a couple hundred years to get one, but it is MD, and it is number over here somewhere. One of these
101.
radioactive ones. Yeah, 101, named after Mendeleev. Mendelevium. He's got an element named after him. Finally, you would think he would have gotten something sooner, but that's okay. So we'll be working through the different parts of the periodic table today. You don't need to know some of the guys here. So John Newlands, I will probably not ask you anything about John Newlands, okay? And when we watched the video yesterday, and hopefully you watched the last 5 minutes of it, please do sometimes this week. I sent you a reminder out. Hank goes through and talks about Mendeleev, and then he says, and to be honest, several other men were working on this at the same time as Mendeleev. So Newlands is one of those guys. I don't like going into another whole big history lesson because in the grand scheme of things, Newlands and these other guys really didn't get credit for the periodic table. You can read about them in the book if you're interested in them. You do need to know this. So I think we finished off here yesterday. The periodic law is, I'll give you my version of it in a minute. The repeated pattern of periodic properties is the periodic law. So I made this into a little tongue twister. Let's all try it together slowly first. Everybody? The repeated pattern of periodic properties is the periodic law. Notice all the P's. It's like Sally's sold seashells down by the seashore. Remember those things? Okay? So the repeated pattern of periodic properties. Just say those words. Everybody? Repeated pattern of periodic properties. Okay? This is the periodic law. And this is what Mendeleev, and to be honest, starting with Dobereiner, started to see. A repeating pattern of properties. And if you can remember that, that's really what the periodic table shows us. Repeated pattern of periodic properties, that's my definition of the periodic law. Okay, now these guys, again, I wouldn't spend a lot of time except for Mendeleev. You don't need to know anything about Meyer. I don't think I've ever put a question about Meyer on a test or a quiz. John Newlands, it's interesting to read about, but the law of octaves, the video we watched yesterday referred to that a little bit. And Moseley was an important guy, but again, unless you're going deeper into the background of the periodic table, I'm not going to ask you questions about that. I will quiz you on Dobereiner and Mendeleev. Okay, I think everybody knows this already, but just a quick review. Name of the element, atomic number, which is equal to the number of protons plus electrons, not added together, but protons is 8 for oxygen, electrons is 8 for oxygen, and down at the bottom our average atomic mass, which remember is the average of all of those isotopes. We covered that in detail, I believe, already. Okay, columns are called groups, so there are 18 groups on the periodic table, and let me grab one here real quick. I like this one because it's nice and colorful. But we have group 1. They have very creative names. Okay, we have group 1, we have group 2, we got group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. These are the group numbers at the top. There are 18 of them. Some of them have special names. We'll cover those in just a minute. The horizontal rows are called periods. And so there are 7 periods, 1, 2, 3, 4, 5, 6, and 7 on the periodic table. These two are not periods 8 and 9. Remember, they fit in here. So they're part of period 6 and part of period 7, just like our energy levels. So the periods here are directly proportional to our energy levels. Everybody, I think, knows that already as well. Okay, groups 1, 2, and 13 through 18 is your S block, and your P block are called the representative elements. They are the ones that are probably the most common elements that we deal with, as well as some of the other metals. Well, transition metals are groups 3 through 12, so that's your D block. Okay, so S and P blocks are called representative elements. Transition metals is the middle block, your D block right here. And they're called transition metals because they transition from these metals over here to these metals over here. Okay, they go through a transition. There's a lot of similarities in these metals, but they're all adding electrons to those D orbitals. Okay, now 3 classifications of elements: metals, nonmetals, and the in-between group, metalloids. Okay, let's define these very briefly. Metals are elements that are generally shiny, bendable, conduct electricity pretty well, usually hard but not always. Solids for the most part, with one exception. What's the exception to the metal that's not a solid? Mercury, okay. And I'm going to pass this around. If anybody is absent today and they want to play with my mercury, you can, but you can't open it up. I like doing that. Mercury is way at the bottom of the periodic table here, so it's extremely heavy. Notice it's only 2 elements away from lead and 1 element away from gold, so it is very dense. And so mercury is really cool to play with, although it does cause brain damage if you play with it with your bare hands. So 50 years ago, chemistry classes would always take mercury around and play on with it on the desktops and stuff like that, but they found out that it gets absorbed through your skin and starts to cause brain damage after extended contact. So mercury's not friendly to chemistry classes anymore. And that is dirty mercury, so I need to clean it up, and I'm planning to make it nice and shiny eventually. So metals are good conductors of heat and electricity. These are some properties of metals. Everything over here from group 1, with the exception of hydrogen, everything that you see on this periodic table in blue is a metal. So everything to the left here is a metal until we get to what I'm going to talk about in a minute, the metalloids. So under metals we have a couple subgroups. So the alkali metals is everything in group 1. Everything in group 1 with the exception of hydrogen is called an alkali metal. So this would be lithium, potassium, sodium, rubidium, cesium, and francium. Special name, group 1. You labeled this on your periodic tables, hopefully with a color or a code or some kind. Everything in group 2 is called the alkaline earth metals. Alkaline earth metals, again, are metals. They're very soft. By the way, the alkali metals are so soft that you can cut them with a knife, which we don't usually picture as being metals, but they are. Can conduct electricity, very low densities for the first couple. Very, 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 very reactive. Alkali earth metals, group 2, a little bit less reactive, still metals. They're called earth metals because we find things like barium and strontium and calcium in the earth. They're kind of chalky, rocky kinds of elements. And then we have the other metals as well. Transition metals is our D block. So everything in the middle here that we usually consider metals: zinc, copper, silver, gold, nickel, cobalt, iron. We picture those as being metallic, and they are. The metals go all the way, by the way, over here to aluminum. Aluminum is pretty much the last row that we would call a metal. And then you have tin and lead over here, which are also metals. Technically, bismuth is a metal as well. Okay, so we have a few metals right over here that are not in the transition metals. They're in groups 13, 14, and 1 or 2 and 15. And then we have the inner transition metals. The inner transition metals is your F block. These are all metals down here. Most of them are radioactive. The whole bottom row is man-made ones, but they are all metals as well. So we have the transition metals and the inner transition metals. Anybody want to take a guess why they're called inner transition metals? Ethan?
Because they're between alkaline and transition.
Okay. I'm not positive that's the reason. That's a great reason. That's reason number one, because they're in between the alkali metals and the transition metals. They're also called inner transition metals because the electrons that we're adding to those ones are going into the f orbitals. And the f orbitals are actually buried, remember, below the 4f. So when we go to this row right here, the lanthanide series, we're actually adding those f electrons after we've already put 2 electrons in the 6s orbital. So it goes 6s, 4f. Remember that? So it drops down 2 energy levels. So we're adding electrons to the inside of the atom, which is weird. Okay, so they're called intertransition metals, I believe, for that reason, but your reason makes sense too. There's 2 names for these 2 F block rows, and you should know these. Okay, so the lanthanide series are named after. Anybody want to take a guess? Lanthanum, good. That's La. Okay, La is lanthanum. It's number 57 up there. And that's what this series is named after. And actinide series is named after the one right underneath it, number 89, actinium. And again, the reason they leave these on most periodic tables is to remind you that those are the first 2 elements of those series. Lanthanum, lanthanide series, actinium, actinide series. And again, it's 14 elements long, fits right in there. And frequently when you'll see a periodic table like this, these last 2 elements over here are actually the first 2 in the D block, right? Because if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 15th one is actually the first one in the D block, which should be here. Okay, so we've got inner transition metals made up of lanthanide and actinide series, F block. Okay, where are the nonmetals? Here's some properties of nonmetals. There's a lot of gases. There's a few solids that are brittle. There's 1 liquid, bromine, and they are all clustered up here in the upper right-hand corner. All of your nonmetals are in the upper right-hand corner of the periodic table, and they don't conduct heat very well. They don't conduct electricity very well. And if you look up here on this periodic table, your nonmetals are the green ones. If you look in the back cover of your textbook, the nonmetals are the yellow ones. So again, color coding here is very nice. Blue for metals, yellow for nonmetals, and green we're going to cover in a second, metalloids. So it's just slightly different colors up here than over here, but the differentiation is still the same. Nonmetals. Now, group 17 has a special name. In the nonmetals, most of those are halogens. So that is fluorine, chlorine, bromine, iodine, tennessine, and astatine. All of those end in INE, by the way. If you see one that ends in INE, it's probably a halogen, group 17. Fluorine, INE. Chlorine, INE. Bromine, INE. Iodine, INE. And then there's 2 more that are kind of rare underneath it. That's astatine, AT, and the newest one down there, tennessine, named after the state of Tennessee. Good. It was discovered in a nuclear lab up in Tennessee, so it's named after the state. We have a special name for group 18, and I think most of you have heard of this one already, the noble gases. The noble gases are called noble gases because, like nobles in medieval Europe, they don't interact with the commoners, right? Where did the nobles hang out? In the castle, yeah. Do the nobles invite the serfs and peasants to their parties? No. No, not unless it's a Bud Light commercial. Okay, no, just kidding. But the nobles hang out in the castles. The nobles don't interact with the peasants. The nobles don't work for a living. The nobles live off the taxes of the others. And so the same way, these noble gases here, helium, neon, argon, krypton, xenon, radon, and oganesson, they are happy the way they are. They've got 8 electrons, or helium in the case, helium-2. They've got all the electrons they want. They're happy. They're living the life. They got every food provided for them. They got the meals provided. They got a castle to protect them. They got everybody who's a noble around them. They are content, so they don't react, right? You know, if you don't have to react with the other things, then no. And that's the noble gases. They don't react with any other elements because they don't need to. Okay, so these are the nonmetals, halogens and noble gases. Okay, now in between the metals and the nonmetals, we have these weird ones, okay? And they sometimes act like metals, and they sometimes act like nonmetals. And they're called metalloids, okay? It's just a weird word that means sometimes metals. Now the metalloids fall on or below what I call the staircase. I'm going to show you where to find the staircase and how to draw the staircase, okay? Let me pull up here a blank periodic table. There we go, blank periodic table. So, right over here are two key elements that you need to be able to find, aluminum and boron. So we've got boron and aluminum. Okay? So right in between those two elements is where we're going to start our staircase. So if you have a staircase, it goes over, we're going to go over right in between boron and aluminum, and down. And over, and down, and over, and down, over, and down. Down. So this is what I refer to as the staircase. Your textbook, I don't think, calls it the staircase. But any element, with the exception of aluminum. Now, aluminum's an exception. Aluminum is going to be a metal all day long, okay? Every other element that is above or below that red line I just drew is going to be called a metalloid. So it's going to be this one, 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 this one. I know sometimes that's called a halogen. Some textbooks refer to astatine as a halogen. Some refer to it as a metalloid. Some just don't talk about it. But it's on the staircase, so I'm going to say it has properties of a metal and a non-metal. Okay, and this one down here, we don't really know about, but it would probably be a metalloid as well, because it's a new element that's only been made in a nuclear reactor, and it's very, very, very unstable. Okay, so all these are your metalloids. Sometimes they act like the metals, which is everything to the left. Sometimes they act like the nonmetals, which is everything to the right. There's only one exception to that rule, and that's Mr. Hydrogen. He's a nonmetal, okay? Hydrogen acts like a nonmetal because he's a gas, okay? Just like helium and nitrogen and oxygen and fluorine, all those are gases. Okay, so everybody should be able to find that staircase and tell me, if I pick an element, any element on the periodic table, you can tell me, is it a metal, is it a non-metal, or is it a metalloid? It's going to be one of those three things. Great multiple choice questions on quizzes, okay? Definitely see a couple of them. So the only tricky ones are the ones that get close in here, okay? Aluminum is tricky, okay? Everything else here, boron would be a metalloid. This is silicon, and then you have germanium, arsenic, antimony, tellurium, polonium, astatine, and tennessine. Okay, any questions about the staircase? On this periodic table up here, it's that black line you can sort of see. It starts between boron and aluminum. In your textbook, it's the green elements right here. You can sort of see the staircase going down that way with the exception of aluminum. And on that periodic table up there, they're the red ones. Okay? What else do we need to know? Let's go back to... What's that? Yeah, just set that before for a second. Okay, now the periodic table here, we've showed you this before. Remember that your F block goes in the middle here. Okay? You got your D block over here, 4 high. You got your P block over here, and you got your S block over here. So remember that the actinides and the lanthanides, lanthanides is the first one, actinides is the second one, fit right in the middle here. Starting with lanthanum and actinium. And technically, these two right here are the first two in the D block, lutetium and lawrencium. Okay? And then we're done section 1. Okay, what row of elements is, what is a row of elements on the periodic table called? Tara?
Period B.
Period B, good job. And let's try this one here. What is silicon example of? Metal, metalloid, or non-metal? Rachel? Si. Metalloid, good. Silicon is one of the most famous metalloids, and because of its characteristics of being like a metal or a non-metal, sometimes it's used in what we call semiconductors. And semiconductors are the basis for all of our electronics today. All of your silicon wafers are made on silicon, obviously. And by doing something special to the silicon, we can make it conduct electricity sometimes or not conduct electricity sometimes. Therefore, it's called a semiconductor. Just like a metalloid. Sometimes it does one thing, sometimes it does another thing. And so silicon is probably the most important of all those metalloids. Okay, let's see what we got here. I'm just going to flip through this real quick so you can see that you know everything in section 2 already. Electron configurations we've already covered. We covered this in the last chapter. And again, I usually pull all of this information back. Here's electron dot configurations, or Bohr diagrams I call them. We talked about SPD and F already. You know that. Again, you can read this part of the chapter if you like, if you want a review on it. But I've covered it already. SPD and F, SPD and F, S block, D block, 5 orbitals, F block, 7 orbitals, and we're done that section. Okay, so again, we're done section 2, and the last thing we'll cover today, and a little bit of review tomorrow, is section 3. So let's dive into that. This was related to last night's homework, which I didn't check yet, by the way, those of you watching on camera. We're going to check that on Thursday, so make sure you have it with you. Okay, atomic radius. What do atoms do? Are they all the same size? So atomic size, by the way, let me cover one more thing on the periodic table before we get past that. Everybody should know solids, liquids, and gases. Okay, well, there's only 2 liquids, and you need to know on the whole periodic table at room temperature. Now we can make any of these liquids if we either heat them up or cool them down. But there's only 2 liquids. Who can name them? Sam?
Mercury and bromine. Good.
Mercury's down here, and that's the one I just passed around in the bottle. And bromine is over here. It's a brown liquid. It's used in hot tubs. You know how you put chlorine in swimming pools to kill germs? The problem with chlorine is it burns off really fast at hot tub temperatures, which is usually about 102 to 105 degrees. So you use bromine tablets in a hot tub instead of chlorine tablets. And what do they paint on your arm before you have surgery in the hospital? Iodine. So they use that brown stuff and they paint it before they cut your skin open. That's iodine because it also kills germs very nicely. So you notice, again, a periodic trend here in one of Dobereiner's triads. Chlorine, bromine, and iodine, all of them kill germs very effectively in our drinking water, in our hot tubs, and when we have surgery. Cool. Okay, let's talk about atomic radius. Now, atomic radius is affected by electron configuration, so we already know about that. Not going to cover that real quick. So when I have, let me find the chart. We'll just talk about the chart here. Let's talk about our regular group S and group P, or our S and P orbital elements here. So notice the pattern here. It's always like teaching with pictures. What happens as I go from left to right? Destiny? What is the pattern?
Oh, they're all getting smaller.
Very good. Okay, so this is what happens as I go across the periodic table. Elements get smaller. We're talking about atoms. So I would say lithium is bigger than beryllium. Literally, an atom of lithium is bigger than an atom of beryllium. Beryllium is bigger than boron. Boron is bigger than carbon. Carbon is bigger than nitrogen. Nitrogen is bigger than oxygen. Oxygen is bigger than fluorine. Fluorine is bigger than neon by a tiny little bit. The little numbers in the upper right-hand corner here get smaller, and those numbers are actually measured in, doesn't say here, picometers. Okay? Remember our pico? Okay? Great monarch King Henry died by drinking chocolate milk Monday night, probably. The probably is pico. It's incredibly small, 10 to the negative 12th of a meter, I believe. So this is 152 picometers, 112 picometers, 85 picometers, 77 picometers. By the time I go from here to here, we're half the size. We've gone from 152 to 73 or 74. So half the size. Why do elements get smaller as we go across? Anybody want to take a guess about this? Anybody read about it last night? We're adding electrons and protons as we go across the rows. So you would think they'd get heavier and bigger. It's true they get heavier. The mass increases. Why do they get smaller though? Ben?
Does the electron get pulled more towards the center because of the more protons?
Okay, so we have an effect going on here that as I add more electrons in the same energy level, okay, if I'm in the same energy level and I'm adding more electrons, they start to get attracted. Exactly, it's an attraction between the nucleus and those electrons. And they get pulled in tighter and tighter and tighter. So there's more attraction between, for instance, 5 electrons and 5 protons, or 15 electrons and 15 protons, or than there is between 10 electrons and 10 protons. So it's a stronger attraction. It starts to hold those electrons tighter. So by the time I get over here to the noble gases, they're really held tightly. All of the orbitals are full. I've got 2 electrons in every orbital, and those, they're really, really, really friendly, okay, really tightly held by the nucleus. So that builds up every time I add an electron. Notice it's big when I go from 1 to 2 electrons, 2 to 3 electrons, and then it tapers off. There's not a lot of difference between 71, 72, 73, and 75. There's a huge difference between 112 and 152. The pattern is the same in every energy level, right? It gets smaller as we go across, and we need to remember that. Now, what's the pattern as I go down the periodic table? Melanie, what do I notice if I compare, for instance, all of these?
They go bigger.
Okay, so they get bigger as I go down the periodic table. How can we explain that? That should be easier to explain. Because what are we adding when we go from here to here, or here to here, or here to here? Ben?
Is there new energy levels?
Yeah, so we're actually adding, remember, a whole new energy level. And remember, the energy levels, according to Bohr, are related to their distance from the nucleus. So when I go from element 71, element neon, to element sodium, notice it jumps from 71 to 186. That's the very next element. Why does one electron jump from a size of 71 to a size of 186? Because it's in a whole new energy level. It's a brand new s orbital, and it's bigger than this s orbital by a huge amount, 152 versus 186. Again, it doesn't sound like a huge amount, but that's almost 30 divided by 150, 3 over 5, 20%. It's 20% bigger, okay? And then I jump up here again, and I jump up here again, and we get some really fatty guys down here, okay? Really big elements down at the bottom of the periodic table, because I got 7 energy levels of electrons. So the trend is, part of your homework last night, what is the trend in atomic size? We would say it increases from left to right, and it increases as we go down. So if you can remember that, then you can probably tell me the smallest element on the whole periodic table is? Anybody? Yeah, hydrogen or even smaller, helium, okay? Helium is the tiniest one. Even though it has 2 electrons and hydrogen only has 1 electron, remember the 2 electrons are held a lot tighter than the 1 electron for hydrogen. So this is the smallest one. Everything in this corner is going to be super small. Where's the biggest guy is going to be? Opposite corner, okay? Lower left-hand corner, cesium. And if we had the 7th row on here, they don't include it because all of those elements on the bottom row, row number 7, period 7, are man-made elements. And they haven't actually had them around long enough to measure them. So those radioactive elements only last like a split second before they disintegrate radioactively. So they haven't actually been able to measure them, which is why you have all those numbers for atomic mass that are approximate numbers. Okay, so the biggest one would actually be francium. If I ask you what's the biggest element in its natural state, the answer would be francium. What's the smallest one? Helium. If you can remember that fact, you'll always remember the smallest are on the right-hand side and the smallest are at the top. The biggest are on the left-hand side and the biggest are at the bottom. Okay? Tiniest, biggest. And that tells you your trend. Good? And again, I can take 3 or 4 screens of words to tell you that, but I love this picture explains it all. Okay? Okay, and that shows the same thing. Again, you could draw it this way. The size increases. Whoa, 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 whoa. Yeah, size decreases, I'm sorry, and size increases. Yes, that's what it says. Okay, so we get smaller as we go across because of the tighter attraction between the nucleus and the electrons, and we get bigger as we go down because of extra energy levels being added. And China added energy level, it literally is farther away from the nucleus. Kind of like Bohr said, but not really because we're talking about clouds of electrons. Okay, what is an ion? We're going to cover this in a lot more detail in the future, but for now I want to see what the pattern of ions is on the periodic table. An ion is anything that loses or gains electrons. It becomes positive by losing electrons, and it becomes negative by gaining electrons. So this is an interesting pattern when you look at this chart that I'm about to show you. Okay, so an ion, what is it? First, you know it's either a positively or negatively charged atom that has gained or lost electrons. And when atoms lose electrons to become positive, they become smaller. Let's talk about why. Number 1, losing electrons from the outer shell. Okay, losing electrons, valence electrons, can leave an empty outer orbital. Let's talk about sodium for a second. 2 electrons in its first energy level, 8 electrons in its second energy level, and 1 electron in its outer energy level. Okay, 1s2, 2s2, 2p6, 3s1. 3s1. So what happens when sodium as an atom becomes sodium as an ion? It loses this electron. Okay, that electron goes and hooks up with a different atom. So guess what happens? It gets smaller. So positive ions are always smaller than their atoms for that reason. It actually loses its outer energy level. This only applies to positive ions. And secondly, negative electrons and we'll talk about this one in a second when we talk about the negative ions, okay? So positive ions always become smaller, mainly because they lose that outer shell. Negative ions, on the other hand, negative ions gain electrons. Why do they get bigger? So we got two things happening. Something that's going to happen on the left side of the periodic table is different than on the right side of the periodic table. So if I gain electrons, that electron from sodium all of a sudden comes over here and joins chlorine, for instance. Chlorine gets bigger, it goes from 100 to 181. That's weird. Why does that happen? Because chlorine now has gone from 7 electrons to 8 electrons. Those 8 electrons are going to push each other apart. Remember, electrons are all negatively charged. They don't like each other. They push away from each other as much as possible. So the more electrons I add to an atom, the further they're going to push away from each other. And it's actually going to make that outer shell bigger. Okay, so we see that positive ions are smaller than their atoms. Negative ions are actually going to be bigger than their atoms. Two different things happening. Now, one of the things you'll always notice is that positive ions are always going to form on the left side of the periodic table. Everything to the left of the staircase are going to form positive ions. Those are metals. They're going to get smaller. Elements to the right of the staircase are going to gain electrons. They're going to get bigger. So we end up with a really strange pattern here. And we'll probably start right here tomorrow and review this because it is a little bit tricky. Tomorrow we'll also talk about ionization energy and electronegativity. And then we'll do some review because then we'll be done with the chapter. Okay? So again, review those two terms, electronegativity and ionization energy tonight if you want. Heads up on that. And we'll see you tomorrow. Cut.